Then we got some practice going on. Number 33, critical numbers of the following functions. So first thing you ask yourself, are there any places where the derivative does not exist? For number 33, no. It's a polynomial. Polynomials are differentiable everywhere. So you set that thing equal to 0. And just looking at it, I'm pretty sure, well, we set the derivative equal to 0. Let's take the derivative like we're supposed to do. 4t cubed plus 3t squared plus 2t plus 1. Set that derivative equal to 0. I have an extra term, yeah. There was no plain old t term. So it is going to have at least one critical value, because if I set this equal to 0, first thing I would do is factor a t out and get 4t squared plus 3t plus 2 equals 0. And now looking at that, I think there are no zeros for that, because we would need two numbers whose product was equal to 8, whose sum was equal to 3, and that's not going to happen. But just to be sure, let's polysolve. Nope, it's just a quadratic. Clear out the old number. Clear out the old number. Clear out the old number. Yep, it has imaginary roots. So the only critical number here is 0. 34, I'll let you do. 35, I'll let you do. I'll do number 40, because I know trig's not always your favorite. For theta minus the tangent of theta. So first thing you ask, is it differentiable everywhere? Everywhere in the domain. And everywhere in the domain it is differentiable. Let's look at derivative. Set it equal to 0. Secant squared. So secant, after all of that, is plus or minus 2, which means that cosine is plus or minus a half, which means that theta is pi over 3 plus 2 pi k, or four pi thirds plus 2 pi k. I'll leave the next one for you to do on your own. We'll meet back. Okay, 34 wasn't too bad. The derivative doesn't exist at its little point, which is where 3t minus 4 is equal to 0. And the derivative everywhere it's differentiable is never 0. This one took up so much room I had to erase and move the next one down a little bit. I forgot to label it. That was number 40. So low, high, the quotient rule we tried. We combined like terms. Set the numerator equal to 0 to figure out where the zeros of the derivative were. I got 0 and 2. The only place it wouldn't exist would be if the denominator was equal to 0, but if the denominator is equal to 0, the original denominator would have been equal to 0, so it wouldn't have been in the domain of the function anyway. Number 40 we did together. 41, I took the derivative, set it equal to 0. This piece, sine of theta is equal to 0 at every n multiple of pi. Cosine of theta is equal to 1 at every 2 pi interval. So every n interval 2 pi. So there are our critical values. So finding absolute max and min, the closed interval method. This is using the extreme value theorem. Remember the extreme value theorem, I'm going to call it the EVT. Extreme value theorem. There aren't many guarantees in this world, but the extreme value theorem guarantees you a max or a min. Okay, I can't spell. You will have a max and a min on a closed interval for a continuous function. I'm going to put that up here. Every continuous function will have a max and a min on a closed interval. Absolute max and absolute min. So first thing you do is you find critical numbers that live in the interval. Then you find the values of f at the endpoints and the values of f at those critical numbers. And then you just pick the biggest and the smallest. Easy peasy.